We will continue the Introduction to VLSI Design class, and today we will talk about circuit families. We already covered the CMOS design in the previous classes or videos. Now we will introduce new design methods like the pseudo-NMOS logic, dynamic logic, and the pass transistor logic. So we will start with pseudo-NMOS logic. It's only one type. It's the pseudo-NMOS. The dynamic logic, under the dynamic logic, there are a few types, and we will cover all of them. And in the pass transistor logic, we will introduce also a new ideas as well. So what makes a circuit fast? That's basically our goal. And as we said in the beginning of this class, we are targeting a good design for a circuit with more emphasis in the good part. So we know that there are capacitance that we need to worry about in any circuit. This is a CMOS design of a two-input NOR circuit. And if there are capacitance there, then we know that the dominant equation is this one, where current is equal to the capacitance multiplied by the derivative of the voltage over time. This means if we rewrite this equation, that the delay, which is denoted by the propagation delay, TBD, is also proportional to C over I, the capacitance, over the current, multiplied by the difference in the voltage. So we should target lower capacitance to get low propagation delay. We should have low capacitance, high current, and also small swing in the derivative or the difference in the voltage. So we don't swing that much. This is also true for logical effort. If you want to reduce the logical effort, you should reduce the capacitance and also have a high current for charging and discharging. So basically from this, the conclusion here is that the PMOS are the enemy because they have high capacitance for a given current. Can we take the PMOS out of the equation? Yes, and this is basically the idea of the pseudo-NMOS design. In old days, the NMOS processes has had no PMOS at all. Instead, we use a pull-up transistor that is always on. So, for example, if we want to make an inverter, we have a PMOS in the pull-up, a single PMOS that is always on, connected to the ground. And down there, you design your circuit the same way we design the CMOS circuit. Now, the issue here is that this transistor always on, the PMOS is always on, and it's drawing current, IDS. And because of this, we have a ratio issue. And to overcome this, one way, this is an experimentation, where they try to find what's the correct ratio for this PMOS, P. If you say that you have P over 2, and you assume that this transistor, the NMOS, is 16 over 2, just for sake of assumption, and they try to find what is the right P to make the curve or the relation between the V input and the V output of this inverter, and we call this before the DC response, to make the DC response looks better. We know that the curve that looks like this is the better one. So it's like something that is that we defined and we discussed before when we have the DC response discussion. So they try to make or they choose B to be 24 and they draw it. and then they reduced a little bit, 14. This is the result, and then they reduce it and they would to 4, and this is what they got. And you can see the more we're reducing the value of P, the better the DC response that we get. So we started with 24 that is larger than 16 because we have this mentality from the CMOS design. So where for an inverter, you have a 2-to-1 ratio for the inverter. So if you have 1 here, you double it. So we started with 24, which is not even double, it's less than double, and we get really horrible curve. We reduced the number until we got 4, which is now way less than 16. And we got like something like this. So the conclusion, we should make the PMOS about quarter the effective of its strength or half the effective width of the pull down network. That's basically this experiment, and we can get this result. That if we want to design any pseudo NMOS gate, the design is not that far from the CMOS. The only difference is that now in the pull-up network, we have a single PMOS transistor that is always on with a certain current running over there. Now, the circuit that you want to design, you design it over here in the pull-down circuit or the pull-down network. And in the pull-down network, as we discussed before, you'll find the function. Let's say that the function is y. To get the function should be something all bar. So we need to make sure that you have this bar, and then you put whatever you have there, you design it in the pull-down network, and that's it. No duality anymore. So you design for unit current or on output to compare with the unit inverter. Now here, because this is always on, there is always current running here. Then the PMOS is fighting the NMOS when there is a path to the ground. If there is a path to the ground, there is also going to be a current here. So you are charging and discharging at the same time. So there is a fight. So there is a goal, and there is a long discussion in the book about this. But or the conclusion that was reached from this discussion is that the current of the N should be 3 times the current of the P to have a proper pseudo NMOS gate. So the current here is 3 times the current over there. To make this current wins when the pull-down network is running, because this one is always on. This is the price that we are dealing with. So for the inverter, if you want to design it, you just put a single NMOS transistor in the pull-down network. Notice that this one is always a PMOS that is always on. No matter what's the circuit, inverter, 2-input NAND, or 2-input NOR, it's the same thing, even with the same sizing. We'll come to the sizing. But now for the design, you have a single transistor here, NMOS. For the NAND, 2 in series. For the NOR, 2-input, 2 in parallel. That's it. Now for the sizing. The sizing of the pseudo or the PMOS transistor is 2/3. This sizing is for the same reasons, to have this relation correct. It's 2/3. Now, how do you design or size this transistor or this circuit, the inverter or the NAND or whatever the gate is? We do it the other way around. Remember, in the CMOS, we look at the pull down and we try to size it, and then we go to the pull up and size it as well. Here we'll do it the other way around because we know this is like a constant. It's always this size. So in the MOS, you just double the size. You just double the size if it's a single transistor in the series from the output to the ground. In the NAND, if it is two inputs, what we do is, since we have two, now we say 8/3, 8/3. Here is only one, so it's 4/3, we just double. The parallel is the same as this one. And so on. If we have, for example, 3, then it's going to be 12/3, 12/3, and 12/3. Now to find the logical effort and the parasitic, because these we need to, or to find these values to get the delay. To find these, one way to do it is to find the logical effort in the down or the pull down network, GD. So we find this one by having this size in the input. Look at the input. We look for the input capacitance. Again, it's the same thing. The input capacitance here is 4/3, and then you divide it by 3 to get 4/9. Similarly, here, you have two inputs. For a single input, let's say A, it's 8/3, and then you compare it to the CMOS inverter, the one that we already know, which you divide by 3. So 8/3 divided by 3 is going to be 8/9. Here, for example, we have 8. It's going to be the same as this one in the inverter, which is going to be 4/9. Now, for the up, what you do is you just multiply by 3. You multiply it by 3 to make sure this is correct. Similarly, here, you multiply it by 3, and here you multiply it by 3. If you want to get the average, you can get it easily. Now, for the parasitic, we look at from the output point of view. And the output is 2. You have two capacitance here that you need to worry about, 2/3 and 4/3. So the summation of these is 6/3, and then you divide it by 3 to get the parasitic, which is 6/9. That's the parasitic in the down. In the up, you multiply it by 3, similar to what we've discussed. Here you have 2/3 and 8/3, which is 10/3. If you divide it by 3, it's 10/9. You will divide by 3 again to compare it to the CMOS inverter, and then you get this one by multiplying by 3. Again here, now the output have connected to this and this node and this node and this node, so you add them together. 4 and 4 and 2 is going to be 10/3. So 10/3, you divide it by 3 to compare it to the inverter, and this is 10/9. And then you multiply by 3 to get this one. And that's how to find the parasitic. You can get the average as well for each one of them. This is the sizing of the pseudo-inputs. This is how you design and how to find the logical effort. How to design first, how to size the transistor, how to find the logical effort, and how to find the parasitic. Now, there is an advantage for the pseudo-NMOS. The pseudo-NMOS draw powers all the time. So if this transistor is on all the times, then there is a static power consumption that's already always wasted all the time. So what happens, one way to reduce this effect is to restrict when this transistor is on by adding or by connecting this input or the gate of the PMOS to an enable. And you can choose whether it's active low or active high, but here we choose that to make it active low. So when you have the enable is equal to 0, this will be on. So now the pseudo-NMOS draw the power whenever the Y is equal to 0. And this power called a static power, and you can calculate it by multiplying the current by the voltage, the IDD multiplied by the VDD. That's basically the disadvantage for the pseudo-NMOS design. Now we will move to the other type, which is the dynamic logic. It's the same problem. We're trying to solve the same problem. Remember, this is the static CMOS inverter. This is the one that we discussed, the pseudo-NMOS inverter. Now we have what we call the dynamic inverter, where now we connect this PMOS to a clock file. So the dynamic gate uses a clocked PMOS in the pull-up. And you have two modes now, pre-charge and evaluate. Whenever you have the clock, for example, this, now we draw the clock. If it is 0, this means that this is on, and what you are doing is you are charging this node at the output. This is why we call it pre-charge. Whenever it is 0, it is pre-charge. And if it is 1, then this will be closed, it's no more connected, and this one here, or the pull-down network, is connected, and now we are doing the evaluation of whatever inputs we have. In our case, this is the simple inverter. So we evaluate, and based on the value, you get the output, whatever value you have in the A. This is the idea of the dynamic logic circuits. Now, also, there is an addition, which is the foot at the end of the pull down, because if you don't have the foot, if this is not there, what happens is, let's go back to this one. What happens is this could be on, and the A is also equal to 1. So this is also on. And in that case, you are connecting the VDD to the ground for some time, for a brief moment of time when you are in the evaluate period. So to make sure that this doesn't happen, we can add the foot, where it is also connected to 5. So when this is on, this is off, and vice versa. When this is off, this is on. This way, the VDD doesn't connect to the ground. So now you have a footed dynamic logic circuit, and you have unfooted dynamic logic circuit. Again, this is the only difference, that you are adding the foot. And for the design, it's the same way when you design the pseudo-NMOS circuit. It's the same exact way. You design your circuit in the pull-down circuit. Okay, let's have some examples to understand the difference between the foot and how to size and so on. To size, for the inverter, the sizing is one of the easiest sizing of all the types of the designs. So it's just 1 and 1. So it's like the pull-up network and the pull-down network have the same size for the inverter if it is unfooted. Now, if, for example, NAND, a 2-input NAND, then you have 2 in series, and you have 2 and 2. If it is an OR, then it is 1 and 1. So here we can say that this PMOS that is connected to the clock have a size of 1 all the time. Now, to calculate the logical effort and the parasitic, we calculate the logical effort same way. We care about the input capacitance, so it is 1, and you convert to the inverter, 1/3. Similarly here, it's 2/3, and here it's 1/3. You can see that it's easy. For the parasitic, we look at the output, and it is 1 and 1, so it is 2/3. In the output here, it's 1 and 2, so it's 3/3, and here we have 3, so it's 3/3. Now, if you add the foot, what happens is you are introducing a new transistor in the series, which means that the sizing will be more. Now in the pull down, instead of 1, you have 2 and 2. Instead of 2, 2, you have 3, 3, 3. Instead of 1 and 1 in parallel, we have 2, 2, and 2. And this affects the logical effort and the parasitic as well. You can find that now the logical effort is 2/3, and here it's 3/3, and here it is 2/3. And for the parasitic, in each one of them, you have here 1 and 2, so it's 3/3. Here 1 and 3, so it's 4/3. And here 1, 2, and 2, so it's 5/3. However, even though it looks simple, it has a terrible problem. It's related to monotonicity, or monotonity. So the monotonity says, or if a gate requires to be monotonically rising, have a monotonically rising input during evaluation, this means that you accept 0 go to 0. So from 0 going to 0, the output, I mean the output, you accept to have it, or the input. We are talking about the inputs here. From 0 to 0, from 0 to 1, from 1 to 1, this is all accepted. The only unaccepted input is if you have from 1 to 0. So this means that we need to make sure that the inputs either stays the same or increase. We don't want a decreasing or a falling input. Either it's the same or rising. The falling causes trouble for us. And this property is the monotonicity. And now let's see what's happening and why is this terrible for us. So if you have phi here, and this is an inverter that is footed as well. So you expect if you have 0 here in the evaluate, you will get 1. If you have 1, then you get 0. That's the expectation. Now what happens is, if in the evaluate, you have this forbidden case where you fall in the input. So it's, but the input was 1 and then becomes 0. What happens is, before in the pre-charge, this value, the output, y, is equal to 1. So it was fully charged. So in the charging, the output is always 1. Similarly here, it's 1. There is a delay a little bit here, but it's 1. Now in the evaluate, if you go from 1 to 0, what happens is, when the input is 1, it was 1 and it stayed 1. That's okay, because what happens now, this will be, the A is equal to 1, so this is on, and this is also on, which means this 1 will be discharged to the ground, and the value will be 0. Now we have the y is equal to 0, and we are still in the evaluate session. So what happens now, you are not connected to the VDD, you are not charging, you are still in the evaluate session. If the input changes to 0, meaning that this is disconnected, the y will still have the value 0, which is not expected for you. This is an inverter. If it is 0, then the output should be 1, and what you are getting is 0. This is like a non-expected result. So it's not an inverter anyway. That's why we don't like the falling in the input. Again, with the same property, the dynamic gates produce monotonically falling outputs during the evaluation. The input must be monotonically rising for the dynamic gate to compute the correct function. So let's say that, okay, we want to connect these two dynamic circuits. Can we connect them without a problem? So it's an inverter, footed inverter, connected to another footed inverter. So it's supposed to be two simple circuits connected together. The output of this one is the input of the other one. So now we have the nodes A, X, and Y. Even if you are careful about the A, like for example, the A here is all the time 1. In the evaluate, what happens is, okay, since you must wait for a certain brief moment of time, which is the delay going through this gate, this delay will cause the X to be 1 and then going to 0. Why? Let's focus on this one. Now, A is 1 during the evaluate session. The pre-charge, it's 1. For pre-charge, it's 1. Similarly, for the Y, in the pre-charge, it's always 1. You are charging up. Now, what happens in this circuit in the evaluate? It looks at the input is 1. So this is connected, and this is also connected. So what happens? It will pull it down to 0. And this, what happens? It's 0. This looks great. The inverter works fine. When it is 1, it's going to be 0 in the output, X. Now, the problem is this delay, this simple delay, causes the effect that we don't like, even if it is very short, which is it's falling down. It was 1 and then 0 during the evaluate session. So what happens now is the same effect in the second gate that we are running away from. It's coming to the second gate. So in this, what will happen is, since it is 1 here, it started with 1 for a very brief moment of time. So it was 1, and this was connected, and this also was connected. So it will drop the whole charging of the output Y to the ground and makes it 0 for a very brief moment of time. Now what happens? You are expecting to go back again because of the same problem. Y is now 0 and it cannot be charged during the evaluation session at all, and it will remain 0. And now it's even worse than before. So what should we do to fix this problem? So there is a lot of research going on at that time. They end up with the following correction, which is the introducing the domino gate. And when we say domino, just remember this. What do we mean by domino? So now we have a domino effect where you go like this. So every circuit, it can affect the other one and the other one and the other one. So now we can connect circuits without troubles if we apply the domino gates. So what happens with the domino gates? We simply say, okay, have a circuit, which is a dynamic circuit. In this example, we have a dynamic NAND circuit, 2 in series. And after that, you must have a static, and I emphasize more, a static inverter. It has to be static inverter. And the static inverter will fix the problem that might be within this node, which is now it's called W. So whatever problem happens in the W, it will be corrected in the X. Even if you face another problem in the Y, that's another dynamic circuit, which is again dynamic NAND. The other static inverter will fix the problem. So basically what happens, now the domino gates, by definition, is simply a dynamic circuit followed by a static CMOS inverter, which is the normal inverter that we know. How is this fixed? We discussed this problem before, which is the problem of the fall here. Now, what happens in the inverter will flip everything during the evaluate session. So whatever you have here, it will be flipped over like this. Now, when you try to get the Y, you can get it easily without any trouble. Because in the evaluate, if the X and the Y is on, you won't have this trouble. So let's say here at the beginning you have 0 and then 1. If it is 0, then X is off. You don't have any link. Y is still equal to 1. So you'll have 1. After sometimes at this point, the X is rising. So now the X is 1. And you have this is also, let's suppose it's to be 1 connected. So you have a path going to the ground, and the Y will be 0. And this is a NAND behavior, a dynamic NAND behavior, where you have 0 is 1 and the 1 is 0. So there is no trouble here. Whatever the W, if the W or the Y have trouble, the inverter will fix them. This have trouble, then the inverter, fix them. And we don't have this terrible problem anymore. So again, the domino is denoted like this. You could draw it, the whole thing. And you call this now a domino AND, dynamic NAND, followed by static inverter equals to a domino AND circuit. So NAND, dynamic, when we put the clock like this, it means that this is dynamic circuit. This is a dynamic circuit. And followed by inverter. So now this is a domino. Similarly, this one is a domino. You can denote it like this, which is easier. This is an AND with the 5, with the clock. This means that this is a domino, which is composed of a NAND and inverter inside. Okay? So now this is the first time that we reach to this point where if, for example, you have you want to design a circuit, let's say the circuit that you want to design is called X. And X is A ANDed with B. So it's simple, an AND circuit. In the domino, what you do is you draw the dynamic NAND or the dynamic circuit. Let's say we don't know what to do here. So you draw a dynamic circuit and nothing here. You can choose to have it footed or not footed, and followed by an inverter. Since there is an inverter all the time, you don't need the bar anymore that we are requiring in all the designs. You don't need the bar anymore. If you have a bar, you need to get rid of it. So now this circuit here is exactly the one that you design over here. And this is what we say, that A ANDed with B is A and B in series, and that's it. So here's the hint that in the domino gates, we are no longer requiring the old bar that we all the time look for in the CMOS design, in the pseudo NMOS design, and also in the dynamic logic. The domino doesn't need that. And we will see some examples. Hopefully it will clarify this. So now you can also use the domino, the idea of the domino for multiplexing. So let's say that you have, this is the dynamic circuit with D0, D1, D2, and D3. And here, this is the other part of the dynamic circuit, D4, D5, D6, and D7. And you want to choose one of them to be in the output. So this is multiplexing. The only things or different than what you expect, you might say that this is D0 to D7. So we have in the mux, we have 8 inputs. So, and we're supposed to have only a single output. So the selectors will be 3 lines. You might think of it this way. But this is a special multiplexer where you have exactly the same amount of the input. So you have also 8 selection lines. And it works as a one hot encoding multiplexer, where if you want to choose D0, you make this on and the rest off. If you want to choose D0. So this is for the selections. Also, this is also like a special kind of multiplexing where after you choose this, now where is the domino play its part here? This is the dynamic circuit, as we say. So this part of the dynamic circuit, it is followed by this inverter. So this plus the inverter is the domino. Similarly for this one, this plus this inverter is the domino part. Since you want to select between this or that, then what you're doing is actually ORing the two paths. Is that the only way to use the domino circuit to design a multiplexer? No, there is many ideas. But that is one of the ideas. The thing that you should be aware of is the value that shows here. If you select D0, so this will be on. D0, whatever the value, there is 0 or 1. Let's say it's 1. So this is on. it will go here, it will be inverted. And from this path here, you will get nothing here from this side. So it will be inverted, and then the result here would be D0 bar. So it's like an inversion or the inverted multiplex. Now, you remember I said that now in the function, we no longer need the all bar in the function or the full bar for the whole function. This is why they come up with the dual rail domino, where you have both the function with the normal polarity and the complement of the function. So you can say that, or you can see here that we basically have the normal function where you do the design over here, and this is the pseudo-MOS connected to the clock, and there is a foot here, and the foot is optional whether you like it or not. And you have an inverter at the end. And you design it the same, and we will have certain examples. Now, what happens here is the complement. If you want to have the complement here, you get the Y bar first, and then again, you get rid of the bar, of the full bar along the whole function, and then you design it over here. This way, you have both the function and the function bar. And this is a simple table to show you all the different possibilities. Y and Y bar, they could be the normal way, which is 0 or 1, 1 or 0, which means here that the value is 0 at the Y, and the value is 1 at Y. If you have 0 and 0, so if you have 0 here and 0 here, it means that before the inverter, you have 1 and 1. And this could happen in the pre-charging, when you are charging the node from the VDD. So you are in the pre-charging if this happens. Now, if you have 1 and 1, this could never happen. It's not supposed to happen. If you have 1 and 1, this means that you have 0 and 0, and this could never happen. So it's in that. So as a summary of what I said, the domino only performs the non-inverting functions. That's the domino. And, or, but not NAND and NOR. The dual rate domino solves this problem. So it takes the true and the complement of the inputs and produce the true and the complement in the outputs. Let's have example to understand the concept of the domino and also the dual rail. So let's say that we want to design and NAND. This is the function of the AND. This is the function of the NAND. The only part here is that we need, if you say that this is Y bar and this is Y, this is the function of Y, this is the function of Y bar, which is the NAND. This is the AND and this is the NAND. Now in the NAND, we should break this line to make it A bar or B bar. We need to get rid of the full bar or the all bar, what I said before. So now you say, okay, now I have the function without a bar. I have the inverter. That's one of the properties of the domino. So the dual rail domino. Now you have this on the Y bar as well. The A and B in series, so you make them in series. The A and B here, the A bar and B bar. Notice that you have bar here. They are in parallel, so you make them in parallel. So the only part that you design is actually this part and this part. The rest is actually the same, no matter what is said. Let's have another example that has another idea, which is the XOR and X NOR. So if you say that Y is A XOR B and Y bar is A XOR X NOR B, then the function of the XOR, we know that it is, this Y is going to be A B bar or A bar B. That's for the XOR. For the XNOR, we know the function already that it is AB or A bar B bar. That's the XNOR. So what happens is you're supposed to have in this design here 4 transistors, since you have 4 laterals. Similarly here, 4 transistors. But if you notice here, we have only 3 transistors here and 3 transistors here. The idea here is that we take advantage of sharing. Take advantage of share. That's the only idea in this design. How? If you want A and B bar, you will get, this is always B here. So you will have A from this side and B. in the XOR. So you have sorry, A bar and B for this one. You get it here, A bar and B. So that covers this term. And for this term, A and B bar, you cover it from this way, A and B bar. So now you cover both of this using shared. Let's say it for the, or get it for the XNOR. The XNOR, we said AB or A bar, B bar. So now you have A bar, B bar here. And you also have the A, B. This is the A from this part. And you have B here going down. So now you know that we are sharing the B and B bars among the XOR and the XOR. That was the idea here. Now, after we finish these ideas that we talked about in different design, pseudo and MOS, and the dynamic logic in a whole, like we talked about the dynamic circuits or the dynamic logic, and we talked about the domino and about the dual rail as well. Now we are moving to some ideas that we need to discuss, and then we'll introduce the last type, which is the best transistor. So the first one is the leakage, and we're discussing this because it happens in the dynamic loads, or the dynamic logic, or the dynamic nodes. So the dynamic nodes floats high during evaluation. Transistors usually are leaky, and this happens if you look here at this node. If this node, what happens is you see that, oh, okay, why this is supposed to be an inverter. The thing is, sometimes when this value is 0, suddenly, after a while, it becomes 1. Even though this value is 1 the whole time. It's supposed to be 0 the whole time. The problem that you might face that after a while, this 0 becomes 1. Why? It's actually because before the inverter, it was 1, and with time, it's leaking its value, and it becomes 0. It was 1 when you are charging. Here, it was 1. Now, let's suppose that this value, like for some reason, like this one, for you kept it 1 for a long time, it's leaking its value, and it's kind of moving toward 0. This leakage caused this behavior, It could be from the charging phase or from the evaluation phase as well. So if this happens, how to solve? How to solve this leaking problem? This is called leakage, as I said. It's leakage of the current, and we will visit this again when we talk about the power consumption later. To solve this, if you know what was the problem is the leakage from the 1 going down to 0. What happens is, okay, if I have a leakage here, what I'm going to do is I will connect this transistor, which is a PMOS, and I will prevent this happening. Whenever you are about to leak, this one about to leak, what happens is this inverter is connected to the output of this. If this is 1, this is supposed to be 0. If this is 0, this will make this transistor, which is called the weak keeper, on. And if it is on, it will make this, even if it is going towards 0, it will make it 1 again. So you are charging this again, even if it happens in the evaluation. And that was the idea here. So you use the keeper to hold the dynamic node, and it must be weak enough not to fight the evaluation. If the evaluation want to do something else, like if you want to change the value to 0, this doesn't fight it to make it 1 again. This is the idea and how we solve. Notice that we just introduce a very simple weak keeper here to solve a problem in circuits, which is the leakage problem. There is another problem that could happen also in the dynamic gates, and it is called the charge sharing problem. The charge sharing problem, it happens in the dynamics case, as I said, and to understand it, let's say that you have two capacitors, and let's say that it's filled with water. So you have a certain two buckets, Cx and Cy, and you fill the first one fully, and the second one is empty, was near empty. And there is a connection between both of these buckets below in the bottom part, and there is a faucet where it could be open or closed. If it is closed, they will remain like this. Now, what will happen if you open it? You know that if you open it, this one will go down and this one will go up. Now, if we take this analogy to the circuits, if this is VDD and this is ground, this will go down up to the midpoint, which is the one that we don't want, VDD over 2. This is the unknown value, and this one will go up, not all the way, it will go up to VDD over 2. That's the problem. So now we have unknown value in both of them, in the X and in the Y. Can this happen in circuits? That was a bug that happens sometimes, like for example, this is a NAND circuit. This bug happens, and the reason for it is this behavior. How to create it? Let's say that you are in the when the phi is equal to 0. So what happens is this one is on. Let's say that A and B, both of them are 0. So this is off and this is off. And let's say that before that this capacitance was emptied, meaning that it was connected to the ground. So it was completely empty. Now what happens now, this is off, and this is on. When this is on, it will pre-charge Cy fully to the maximum. And Cx is disconnected, and this is why it is empty. And this faucet is actually A, which is 0 now. Now, what will happen if we open A and only A? So what happens if you go to the evaluate session or the evaluate clock? What happens is this will be off, and this one, the faucet is open, on, and the B, we kept it 0. So now the behavior that I just mentioned happened. This goes down, and this one will go up. So the Y is actually feeding the X. The Y is feeding the X, filling it halfway by half of its capacity. And this happens, as I said, when A becomes 1, it was 0 and then becomes 1. Y doesn't go all the way down to 0, it goes middle way, and X, it goes up to the middle way. And this is what we call charge sharing, meaning that they are sharing actually the charge in the capacitance. So Y is the given part, and the X is the consuming. So to find this value, if you want to calculate it, Vx will be equal to Vy, which is Cy over the addition of both of them, Cx plus Cy, which is a certain percentage of the VDD. Now, what's the solution for this problem? We know that the problem is the consumer, which is X. So we need to do something about X. So the solution is to add a secondary point here, where it is connected to a secondary pre-charge transistor. So whenever you are charging Y, you charge X as well. If there is any other node that could cause a trouble, you charge it as well. So that was a simple solution. Add the secondary pre-charge. Typically, you need to pre-charge every other node that could cause a trouble. This big load capacitance, Cy, helps as well. If you make Y really huge, so it could feed the other nodes without losing its logic value. There is other problems like the noise sensitivity, and it happens in our circuits. So there is many sources. Some of them we discussed, like the charge sharing, like the power supply node, and some we will talk about them later, like the capacitive crosstalk, especially in the wires. And there are so many more. There are not only these four. There are so many types of nodes. So basically, what to do with the noise? If we have noise, what to do? If the noise doesn't cause errors for you, you simply ignore. If they cause error, now you need to tackle them, do something about them. Maybe if you can detect the error, you can correct it. And there are so many other methods. So that was the domino. Basically, we talked about the uh, monotonicity, the leakage, the charge sharing, the noise, and so on. And know that the leakage and the charge sharing part, it was a big trouble at the time. And then when they found the problem and they solved it, they found out that the solution is really easy. Now we will move to the last type, which is the bass transistor circuits, the bass transistor circuit. So we actually introduced the bass transistor before, and we said that it's like switches. And this is like for multiplexing, you have A and B. This is one bass transistor, that's another bass transistor, and we can generate the Y. And that's another one where you have an inverted mux, inverted mux. Now, this one has a trouble, which is the non-restoring factors. So whatever noise you have here, you have it in the output. This one, because it has the inverter, it doesn't have this problem. These are what we discussed before. Now the new type is called LEAP, which is short for lean integration with bass transistor. You get rid of the PMOS completely. So now you are reducing the number of transistors used. And then you use the same idea that we discussed, which is the weak pull-up transistor when we talked about the leakage. So now you have this PMOS connected here because the problem is the degradation that happens in the PMOS. If you have a PMOS on, you have another PMOS on, you have a problem with degradation. The degradation of the PMOS happens when you have a certain value. The value is, if you have 0 in the PMOS, since the PMOS is in the pull up, if you have 0 and you have a PMOS, you will have a degradation. Now what happens is we take the PMOS completely away and we left only with the NMOS. Now we got rid of the PMOS and all its problem. We are ending up with only the NMOS, and it has a problem. The problem is when A is 1 or B is 1. Now the 1 will be degraded. So you don't have 1, you will have a degraded 1. This degraded 1, you can fully make it a full 1, let me say, is by having this PMOS connected to the source of the VDD to fully charge it and make it 1 again. 1 again. How to do this? If this is 1, after the inverter is going to be 0, just connect it to the gate and this will be working. It will be on and it will keep charging this one without any problem. So that was the idea of the leap. Not only we protect it against noise, so the noise doesn't go there, we also remove the PMOS, and we have, if you have many PMOSs, you remove all of them and you connect to a single PMOS. So that's a good design. We also have another design based on the same idea, which is the CPL. Basically, the complementary bass transistor logic. The idea here is instead of, it's actually the same idea, but here we have Y bar and Y, instead of having only Y bar, because some will complain like, okay, we have Y bar, we want Y. Then you have both of them here in CPL. Now, if you have Y bar here and Y, again, we get rid of the PMOS. The problem is when these values, the A and B equal to 1, if they are equal to 1, that's a problem. So what happens is you have a VDD here that's charging both nodes that might cause a trouble when they have a 1. So what happens is this one will be connected to this value. How? How is this happening? If the one here is the one that might be degraded coming from here or here. If it's a 1, then here it must be 0. If this is 0, then this must be 1 because you actually have A bar and B bar in the input. So this must be 1. If this is 1, then must be 0, and 0 will connect to the PMOS and fully charge this one again. And you can do the same intuition in the other node as well. That's the idea of the CPL. Just to remember it, remember that it has an X shape connections to connect to the PMOS. Now, as a summary for the BAS transistors, and we talked about this, research and investigated BAS transistor logic for general purpose application in the 90s. Benefits over the static CMOS were small, or sometimes it's worse. No longer generally used. It is used actually, but very, very limited. However, BAS transistors still have an niche in special circuits, such as memories, where they offer small size, and the threshold drop can be also managed. And we will see some of these ideas later when we talk about the memory. Now, we'll give you some exercises just to refresh your mind. If you are asked to sketch a pseudo-NMOS, even if the circuit is very long, don't be alerted, because now if the only thing that you need to worry about is that to have the full, if you have the full bar for the pseudo-NMOS, whatever under the bar, you design it in the pull-down circuit without applying the duality, because in the pull-up, you have the PMOS always connected, that's all. So B and C and D, they are parallel serially with A, that's parallel serially with A. E and F and G, they are series, and the two groups are parallel, and that's it. That's the reason. If you were asked in the second question to sketch a pseudo-NMOS for the 3-input NAND and NOR gates, we already covered the 2-input NAND and NOR. What about the 3-input NAND and NOR? And how do you size them and find the logical effort as well? The sizing, you have this one, 2/3. You have this one, 2/3. Now, the NAND, 3 inputs, 3 in series. The NOR, 3 inputs, 3 in parallel. That's it. Remember, this function, the Y here, is actually A, B, C, all bar. This bar is there. Whatever under the bar, A, B, C, we put it in series. Similarly for the NOR. Now, for the sizing, we said that if it is if this 2/3, if it is only 1, it's going to be 4/3. If it is 2, 8/3, 8/3. If they are 3, then they are 12/3, 12/3, 12/3, which is actually 4. This one is fairly easy. It's 4/3, 4/3, and 4/3 because they are parallel. Now, how to get the logical effort? You find the logical effort for one of the inputs, for example, this one. So it is 12/3 over 3, or you say just say 4/3, which is this one, and you multiply it by 3 to get this one, which is the one in the pull-up network. You can get the averages. For the 3-input NOR, you have one of the inputs. The input capacitance is 4/3. You divide it by 3 to compare it to the inverter. It becomes 4/9. And you multiply it by 3 to get this one. And that's it. You can average them as well. So this is also just the next step question for the pseudo-NMOS. Now, if you were asked to sketch the dynamic footed and unfooted 3-input NAND and NOR gates, and you need to size the transistor and find the logical effort. Okay, you get the unfooted and the footed for both the NAND 3-input and the NOR 3-input. Again, the NAND A, B, and C, all bar. This is dynamic, so we need the bar. We take whatever below the bar, and we have them in the pull-down network. The only difference is now you connect the PMOS to phi. That's if it is unfooted. If it is a footed, you connect the phi also to another transistor in the pull-down, which is the foot. Now for the NOR, they are parallel, and you can add the foot like this. Now for the sizing is one of the easy sizing in all the designs as we mentioned. So now you have 3 transistors, so it's 3, 3, 3. 4 transistors, so it's 4, 4, 4, and 4. Here you have a 1 in series, or 1 to the from the output to the ground. So you have it as only 1, and these are parallel with it. Here you have 2, so it's 2 and 2, and these are parallel with this one, so it gets the same size. So how to get the logical input, but only the down? The GD is equal to, you get the input capacitance here. So it's 3/3, which is 1. The input capacitance here is 4, so 4/3. Here is 1, 1/3. Here is 2, so it's 2/3. So this question is also like an extension question, and it's very easy. For this one, you sketch a 3-input dual rail or a NOR gate. We covered AND and NAND, XOR and XNOR in the previous slides. Here it's OR and NOR. So what happens, you can pick any one of them. I picked it differently. So I make this Y and this one Y bar. What is Y for the OR? It's A or B or C. There is no bar, good. Here we have Y bar, which is the NOR, which is A or B or C, all bar. This is what you are supposed to have. You should break it down. So you break this line, A bar, ANDed with B bar, ANDed with C bar. That's the function. Now you get this, and you draw it in the pull-down network. You get this, and you draw it in series 3. Notice that they are bar with the complements of A, B, and C. A bar, B bar, and C bar. The foot here is optional. I never said anything about the foot here, so it's optional. Now the last exercise, and this is basically like a design problem with certain properties. So let's read into it and try to understand it. So it says design a domino circuit to compute this function. Good, it's domino, and there is no bar. That's good. As fast as possible. And it further says each input may present a maximum of 3 lambda. So that's the input. And the output is 500 lambda. Also, it mentions that choose the transistor size to achieve the least delay and estimates this delay in lambda. That was the requirement of this question. Now, one keyword here is as fast as possible. That was my design, my idea. Looking at this, you should think about it a little bit. What I reach is that we should consider a high skew inverter and a footless dynamic logic. Why? First, he said domino. I know the domino has this one, all the domino circuits with the same sizing, and it has an inverter at the end. And we designed the circuit without a bar, which is this one here. So let's design it. A or B, that's the A and B in parallel. C or D, C or and D in parallel. And they are ANDed together as a group, and they are in series here. That was the design. Now, the only thing that I added here is that first, I'm not having foot, because if I have a foot, the sizing will increase and the delay will increase. And I want it to be as fast as possible. And the other thing, I make this transistor a high skew inverter. Why a high skew inverter? Why not a low skew inverter or a normal inverter? Again, for the same reason, I want it to be as fast as possible. Where is the critical input for the inverter? Is it this part or this transition or this transition? It comes from the circuit before that. You know that the evaluation happening from the pull down. So if the evaluation happened and there is a connection here to the ground, the value is going to be 0. And if the value is 0, then this one is going to work. If the transition in the pull-up network, the one that is charging the output and the critical one for me, or then I should favor this transition. I should favor this transition, and this is why I said I will consider a high skew inverter. Now, after this discussion, I can do the sizing. The sizing here is 1, here is 2 and 2, and this is in parallel, so it's 2 also. 2. I can size this one as well because it's an inverter, it's 2 to 1. Because I sacrifice this one, it's going to be half. Now let's find the delay. There are many methods. One of the easiest one is using the logical effort idea. Now the logical effort idea says that I need to find the logical effort for this one and the logical effort for this one. For one of the inputs, let's say A, it's 2 over 3. So that's the logical effort for the first one. The logical effort for this one, as we explained before, since this is since I care about this input, then I just find the input capacitance here. And the input capacitance is 2.5 divided by 3, because this is what I care about. 2.5 over 3 is actually equal to 5 over 6, which is this. And now we get G. H, it's given actually, 500 divided by 30. The branching, there is no branching here, so it's equal to 1. You can multiply those 3 and you get the F capital, 9 volt. To get F, you know how many stages. You should know how many stages you have here. You have 2 stages, if you are confused. You have 2 stages, stage number 1 and stage number 2. So it's the square root of F, which is 9.3, which is around 3. We know that the square root of 9 is 3, but the 0.3, you just get rid of it. So the parasitic is actually, you find the parasitic in this node and also in the output node. So you find the parasitic in both of them. In this one, you have 1, 2, and 2, so it's 5 over 3. And in this one, it's actually 2.5 over 3. Same idea, it's going to be 5 over 6. You add them together, it's going to be 5 over 2. This is the parasitic. Now you can find the delay. And that's what he wants. He wants to estimate this delay in lambda, and we will do that. So we say that the delay is equal to 2 times 3 plus, which is 2 stages. 3, this is the F hat. And plus 5 over 2, this is the parasitic, and we get it 8.6 tau. This is what the way that we want to find the delay in the using the logical effort idea. Now we find the delay. How about the sizing? Now we said that now it's 500 in the output. So here it's 500. And here in the input, in any input, it's actually 30 lambda. So in every input, it's 30 lambda. And you know that the sizing, they are the same. Then there must be 30, 30, 30, and 30. If this is 2 and this is 1, if this is 13, then this is 50. So you get the sizing quickly for this one. For this one, you need to find the node here. And to find this node, you should calculate it this way. You go backward, 500 times the logical effort here, which is 5 over 6. There is no branching. Good. You divide by the F hat, which is 3. And this is equal to 137. Now distribute that 137 among those 2 based on what you have in the original sizing. So what you do is you say, okay, I have in the PMOS 100. Do it, give myself more space. So in the PMOS, you have 137 times the summation of those 2, which is 2.5. So you have 2 divided by 2.5. And in the NMOS, you have 137 times the summation of both, which is 2.5. And you have only half in this one. If you calculate this one, you'll get 110. And if you calculate this one, you'll get 27. And you can compare, add them together. There should be 137. I'm sure I did some estimations there as well, or some rounding. So that was the exercise. I understand if you didn't do the high skew part. So that's your way of doing it. You consider that this is as fast as possible. that was what I reached. That was the delay that I reached. If you can find better delay, you are welcome. So the last exercise is actually an easy one. It's about the pass transistors. It's simply sketch a 4-to-1 multiplexer, and you are giving 4 data signals D0, D1, D2, and D3 with 2 selection lines, S0 and S1. How many transistors in each design? If you design it in 2 different ways. The first way, use only static CMOS logic gates. So you did the multiplexing this way, and we discussed this before. So you have D0 with S bar, D1 with S, D2 would be with S bar, and D3 with S. You have S0 close to the input, and S1, which is actually the other way around. S0 is the least significant bit, and the S1 is the most significant bit. And you do it for this one as well, same idea. This is actually the same circuit as this one. Now, what about the transmission gate? The transmission gate, we know that we can do the multiplexer this way. So you have 4 transistors for the 2 transmission gate with 4 transistors, and this is a multiplexer, 2-to-1, and this is 2-to-1, and this is also 2-to-1. Now, yeah, notice that, for example, here we use only one inverter, and we get the result this inverter, and we also feed it here. So we didn't have to use another inverter with this one. For the second part, we have to use an inverter. Another idea that we need to look at is the bubbles here. You can have the bubbles at the inputs here, or you can reverse this design and make the bubble all the way in the output by applying the De Morgan law. This is not entirely the same as this one. You know that. But the thing is here, he said, how many transistors does each design require? So let's find how many transistors here. This is a compound gate. And we know we have 4 inputs, so we have 4 inputs in there. Pull down and four transistors in the pull down and 4 transistors in the pull up for this design. And we have the bubble here that tells us that we are fine. So here we have 8 transistors, here we have 8 transistors, and here we also have 8 transistors. And we have 2 transistors here and 2 transistors here. For this design, we have 4 transistors, 4 transistors, and 4 transistors. So it's 4, 4, and 4. And you have 2 in this inverter, 2 in this inverter. So to get the total, you have 8 times 3, which is going to be 28. Sorry, and you have also 2 in the inverter. So the total, you have 10 here and 10 here and 8, so it's 28 transistor. And for this one, you have 4 and 4 and 4, and you have 2 and 2. So you have here you have 6 and 6. So you have 12 and 4 more. So total is going to be 60. Now, if you look at this from another angle, this has actually advantage because it's actually restoring, but this is non-restoring. So the noise will show up at the end. If you want to fix the non-restoring, you have to add an inverter, and the design will be slightly different because the output now is inverter. That's one way. And also you are adding 2 transistors, so it becomes 80. If you want to get rid of the problem. This is what we want to cover, and I'll see you next time with another subject. Most likely we will talk about the wires, which is the second important part of this course. We said that we will talk about the transistor, which are the little things all the way down your design, and we also need to talk about the wires, which is many layers above these little transistors. So that's what we are going to cover next time.